So I just do that and divide by the t. So this is gone now, right? So that's the rate. So I just wrote down the same thing, but coming down to this part, this is now the new formula. That is essentially the force. And then I'm going to draw your attention to here. Area divided by force. What is F divided by A?
Pressure.
So we are getting somewhere. So with all this equation down, I think it's just the one. I think a good practice for you to get to here, and then you will see pressure, which is a force divided by area. There's a volume N, and then I'm going to see this mass of gas by Avogadro's number. That is, we call the molecular weight or molar mass times Vx squared. So, seemingly very complicated equation, but I'm going to highlight the one that is makes most relevant. You start to make the volume with the pressure. I am going to skip this part, make this equation. Looks similar now. Looks okay to you now? You guys know pressure times volume is NIT. I think you just memorize it all the time, right? From this, the simple, very simple derivation, I'm just saying that that's mdx squared. What's that telling you? Yeah. So I use this notation. Physicists use this. They are proportional to temperature. And I can put down a little bit here, saying, well, just multiply by a certain constant. This is what do you call this? Kinetic energy, right? So the quantity V squared is going to be kinetic energy, and that's going to be proportional to the temperature. So sometimes people call big M, small m. This is a per mole mass, or small m is per one molecule mass. Just a conversion by small m times Avogadro's number, you will get this mass per mole, right? So that's just nothing but those relationships. This is a mass per particle, this is mass per mole. That's a correlation. And then I just have to correct a little bit here because this is a V as a vector, is a X, Y, and Z component, right? We just talked about the Vx, so V square is Vx square, Vy square, Vz square. Essentially, we just took it as our convenience. So I can say this is essentially 3 times Vx squared. So therefore, Vx squared is 1/3 of over a speed squared. So I'm just giving you this sort of the equivalent. X, Y, Z is indistinguishable. And we are not really looking at X component. we are looking at overall velocity, and that's just a small correction that you have to go through. And then I just want to essentially say that that's all I need to do. So all of a sudden that in the pressure-wise, this collision, what governs is momentum change in the x direction, but at the same time, that gives a pressure for these surfaces to experience. But this is the one where the speed itself is the one that we want to know. Okay? We are not interested in x component of the speed. So for that, we're just simply using this kind of comparison. Okay. And you guys remember that they are all moving at different speed, so we need to kind of average them. Have you seen this notation? It's like a triangle bracket. We are doing the average value. Okay, that's an average on the quantity. So that's the quantity. So I know that, so I'm going to do the average value. Average value. That's an average value. That's an average value. So the one that I just show up here was essentially an average value. Okay. From the individuals, and then I'm going to say, okay, there's a distribution, so this is an average value of velocity, and that's the final equation that we do. And then you come up with this. Okay, let me say average speed. Okay, and then you will start to see some confusing expressions. When you hear this, when I say what is a mathematical formula for average velocity, that should be simply this, right? But I'm telling you, sometimes this average is meaningful. And here's an example of average velocity square. But there is a mismatch in the units, so people do the square root. And this one has RMS of average velocity. So it has what is called a VRMS. Do you know what RMS means? Root mean square. Okay? Root mean square. It comes actually quite a lot in this RMS averaging it. This is to you is a kind of strange way of averaging it, but this is much more natural way to do the average on the quantity, because V square is the one that we don't have to worry about the signs and so on. This is a root mean square. This is a square. You do the square, and you do the mean, and then later you do the square root, right? So that's a square root mean square. How's it? Okay, so all right. So I said a lot of things, and this is I think it's a little jump ahead kind of idea. But what I'm saying in a nutshell is the following, and I can summarize this. Kinetic energy proportional to temperature. And there's an average velocity squared, right? So the way that the speed, and they have a different mass, and sometimes they can say molar mass times velocity squared. So this average velocity square and the molar mass is essentially constant for a given temperature. Okay? So I start to have this relationship. If I have gas molecule that is, let's say, gas A, and this is a gas B, and their mass ratio is, let's say this is I would just say 100 grams per mole, and this is, let's say, 5 grams per mole, right? That's the ratio. And the actual velocity average will be, if this is, let's say, I'm going to say, I'm just saying that the average velocity is 100 miles an hour. And then you can have a, you don't need any more information because the ratio between the mass is about 20. And if you do this, same kinetic energy, so M1 over M2 is V1 square, V2 square. And then this ratio is 20. And then I said first one is 1,000. So this is 1,000, 1,000 to the 6. And then you will see the 20 and to the 6 as a square. And then so therefore the velocity on this one, which is a V2 root mean square, it's square root 20 times 1,000 miles an hour. So that's a relationship keeping, this is sort of the balance it out. The way that how fast the gas molecule is moving and their mass is they're compensating out. They can have the same kinetic energy, so each impact is essentially the same. It's going back to the original statement about partial pressure, whether this gas molecule is hitting the wall, this gas molecule hitting the wall, exerting the same momentum change. So thereby we don't really count which one is hitting, we just count the number of gases regardless of the sizes. Okay. All right.